Welcome everyone. This is the last video of the test series where I test the TEC12715 unit. So this is the 15 ampere unit, and what I'm going to do is similar to the previous experiments. So I have this polystyrene box here, and inside that there is a Peltier cooler which is cooled by water. You can see the hose is here. And the water-cooled Peltier cooler's cold side is attached to an aluminum container which weighs 87 grams. And this 87 grams of container contains 100 grams of water, which is around 28 degrees Celsius. I will turn on these other devices and we will see the exact temperature, because there are 3 thermometers in it. 2 thermometers, one at the top, one at the bottom of the container, and one in the middle, which is a K-type thermocouple. These two guys are based on the TEC12715 digital thermometer. I really like those thermometers because it's very easy to use them. So those are immersed in the water, slightly touching the wall of the container as well. So they will show us the temperature, and what the goal is to cool down this system to 0 degrees and then let it run for roughly 1 hour and see what happens to the water inside the container. So what you can see here, let's start with the devices which are on. So we have a watch just to keep track of the time, and this 28.8 degrees is the water temperature measured in this flow indicator, and then this is my power meter dash temperature logger. So I log 2 K-type thermocouples temperature, and the current and the voltage is also measured within this box. So I run the power through this box before running it towards the, or letting it run towards the Peltier cooler. So that means that all the current which is passing through the Peltier cooler has to pass through this one as well. So that's how I measure the power. So first the power supply comes into this box on the left side of it, and then it comes out on these 2 contacts and go to the Peltier cooler, and then I just clip on these banana plugs, and that's all. And this small tiny box is another project. It's a 4-channel thermometer, and it's connected to 4 DS18B20 thermometers. So the two of them is connected to the, or immersed in the water of the container. The third one is inside the water tank of the water cooling system, so the temperature will be very close to this. And then the fourth one is behind the radiator of this water cooling system, so it is measuring the outlet air temperature of the radiator. And the fans, which are 2 12-centimeter fans, are attached on the radiator in push configuration, so they push the air through the radiator and not sucking through it. So this is in push configuration. So you see everything. So now we have the 15 ampere unit, and for the 15 ampere unit I determined the maximum current, or the minimum current, the maximum current where I can run the device to reach the lowest possible temperature without any kind of load. So in a previous test series I determined the minimum temperature of this 15 ampere unit by measuring the current and the temperature of the cold side, and I changed the current, and I always checked what is the cold side, and this was done without any kind of load, thermal load, so nothing was attached to the cold side, and it was also insulated. And now I will do the same. So from that measurement I determine the T min, I min. The values are here, but I can tell you. So the minimum temperature was around minus 17.5 degrees Celsius, and the corresponding current was around 10 amperes. So what we will do is I will apply 10 amperes on this device and see how long it takes to freeze the water, basically. Because now we have a load, which is the water and the aluminum tank, and that will change, or should change, everything. So we will see how it changes the situation. So first of all, I start the loggers by connecting them to their power supply. So this will be the thermometer, and it's on, and this will be the power meter, and it's on. So both of them are waiting for the command. So I start them. So this is now writing the file, and this is now also writing the file. So what I have to do, I have to connect to the power supply, which I did right now, and I start up the power supply, which I did now, and we go until 10 amperes. So we are roughly at 10 amperes, but we can check it with our favorite clamp meter. So let's check it here so you can see it. 10.2, so I can slightly decrease. 10.1 something. We can leave it here. So this is now 10 amperes, let's say, and I measure the voltage at different points of this circuit. So first of all, I measure it between the clamps, so clamp 1 and clamp 2, and you cannot see it, but 10.9 volts. I will try to make it visible for you. So 10.9 here, and if I measure the power meter, that is 14.6, and the power supply is showing 15.3. So we have different voltage drops due to the different connections. So we will see. But now I connected everything, and the temperature is dropping now, as you can see. So we are just waiting for 10 minutes from now. So now it's 45. Let's come back at 55 and see what happened to the device. So let's see what happened after roughly 10 minutes. So what I can see is that the temperature measured by the digital thermometers, which are connected to this unit, are 3.7 and 5.0 degrees Celsius. So we could not even reach 0 degrees. And also the K-type thermocouple is showing 2.8 degrees Celsius, which also suggests that we are above 0 degrees. And if you check the water temperature, that is showing us that the water is much warmer, or at least noticeably warmer. I think it's like 2 degrees than previously. So there is more heat introduced to the system, and that's quite obvious from this number. So just the I times U is already 147 watts. So that is quite a lot. And let's just check the current. So what I do, I not only check with this, but I do a measurement on this, and it's like 9.93, 9.91, and then I measure the voltage at different points. Let's see. So I try to let you see it. So plus and minus. So this is 10.9, and then inside here it's 15. And I can feel that the wires are pretty hot. That's not a good sign. But of course they should withstand this 10 amperes. They are rated for that. But it's hot. So what I suggest is that let's wait for 10 other minutes and see what happens. And if nothing significant happens, I might stop this experiment because the wires are getting hot. I'm just not so happy about that. But let's see what happens in 10 minutes. So we are back after a bit more than 10 minutes, and I can see that both of these devices are now very close to 0 degrees. So the top device here, the thermometer here is 0.3, and this guy here is jumping between 1 and 0.8 degrees Celsius, and the K-type thermocouple is at 2.5 degrees Celsius. And I can already see some ice forming in the water, so the water is getting a bit turbid, but it's not too icy. If I knock it, I just see some ice crystals, and they seem to grow in a bit different way than previously. That's interesting. But nothing has happened for real. So what I will do, these wires are still hot of course, but I think they will survive. And interestingly, these wires are not hot at all, so that's very curious. Yeah, so let's run this system for another 10 minutes and see how the temperatures are developing and what is the situation of the ice inside this container. So let's come back a bit later. So I waited again, but the temperature doesn't really want to change. So we see that 36.5 and 37 regarding the water temperature, and if I touch the tank I can definitely feel that it's hotter than the surrounding air or the room temperature, and it's quite hot here now. I can feel it. So the water is still not below 0 degrees, and that's now really confirming that I was saying in the previous video where I was testing the 10 ampere unit. So now, since we are about the unit with the 8 amperes, and this is now the 15 amperes, so almost twice as much in amperes, we need higher currents, or we are applying higher currents, which automatically result in a higher power, and that power appears in the water cooling system. So if we try to reach the same DT value with the 15 ampere unit as we would like to reach with the 8 ampere unit, we will see that the 15 ampere unit should run at much higher currents. I will put an image here as a comparison, and you will see it, what I'm talking about. And because of that, there will be much more heat generated by the 15 ampere unit because of the higher current value which is running through the device. And because of that, you have to maintain better cooling for the larger devices. And this is why for example, the 15 ampere unit looks worse. No, it's not worse than the let's say lower number units. Your cooler is not good enough to keep up with the generated heat, because at the end the advantage of the 15 ampere unit here is that you can increase the current to much higher values, which will allow you to generate higher values for the QC. So you will be able to pump more heat, but for that you will also have to provide better cooling for your device. So it's not worse, your cooling system is bad, and not the device. I saw it in some places that some people said that the 6 ampere unit is better than the 15 ampere unit. That's not true. It's entirely bad idea. The thing is that their cooling system is not good enough, and therefore the 6 ampere unit looked better because that was running at a lower current value, and that was running with let's say better performance due to this. Because if you have insufficient cooling like I have now, because you can see that I cannot even reach 0 degrees, however some ice is forming in the box, then you just cannot work with these devices. So for this system I will stop this experiment because yeah, I'm just producing a lot of heat and also I guess very high electricity bills now. So I stop the experiment here and I will go to the computer and evaluate the available data that I've been collecting, and we will see what we get. And I will also do some calculations, but this is basically the final test of this test series, the freezing series, and we could see that again, I think the 8 ampere unit is the best, but that will be in the next video. So I suggest you to subscribe because you can see it in my next video that I will compare the 5 different units regarding their cooling or freezing performance. So stay tuned. And now let's go to the computer and see what the numbers are telling, which I've been collecting for like 1 hour almost on these SD cards. So let's go to the computer. So check what is our result and check some curves. So on the left side here we have all the thermometers. I also added the K-type thermocouple, which was attached to the other device, and I just added the cold side temperature from that. So let's go from the top to the bottom. So the red curve is obviously the water temperature, and you can see that that goes up to like 36, 37 degrees Celsius. So that's like relatively high. And then the outlet air temperature is also like 35, 36 degrees Celsius, so it's almost the same. And if we go to the other side, we can see, first of all, let's see what's the beginning temperature. So that's 29 degrees. So this will be the T0, what we will use in our formulas to calculate the delta T, which is not the DT, this is the delta T. That's the temperature difference between our initial and final temperature. So between 29 degrees and 0 degrees, let's say. So we turned on the power and set up the current and everything, and we could see and we can see here that there are two sets of curves, and we have this light green, and that is going much steeper down, and that is because I already explained that that's a smaller piece of wire. So it's very easy to change the temperature of that small wire, so it will follow the fluctuations or the changes in the system much quicker. However, we have these two other curves, and they are following the changes much slower than the K-type thermocouple, but they move roughly the same. And when they have to start, when they start to develop differences, that is because of the different position of these temperature sensors. And then what we can see, there is a slight bump here around that's 16 minutes, but we are still well above 0 degrees, so that cannot be anything. But here, that's a very, very strong hint that everything is changing. So you see that there is a significant jump here in the K-type thermocouple, but you can also see that there is a small jump, and this also does a small change or leveling off at this, which is roughly, let's say, 23 minutes. So this guy needed 23 minutes to cool down the water to 0 degrees, which is very, very, very bad. And I will try to explain why. So when we look at these devices and we look at this curve on the right side, we see that we were running it here. The power supply was set to roughly 14.6 or something like that here, as you can see, and that is 14.6 volts, and the current was roughly around 10 amperes. So if you just multiply these two numbers, that is 146 watts. So this is only the heat load which is produced on the back side or the hot side of the Peltier cooler, plus we have a few tens of watts, let's say 30, which is the QC. So the product of these two things, let's round it up to 180. So 180 watts has to be carried away and that is on the hot side of the Peltier cooler, and that is in physical contact basically with the cold side. So if your cooling is not so efficient, then you cannot remove this much heat, and some of the heat will basically like creep back to the cold side and decrease the efficiency of the cooling. And that's what basically happens here, I assume, because now we are running much higher current through these devices. For example, in the case of this 15 ampere unit, or the previous video where I had 10 amperes, when I had the 10 amperes unit and I was running 6.8 or something like that amperes through it. So the higher the current, the higher this P term, and therefore you have to have better cooling. And this has nothing to do with the transferred heat, in that sense that it's independent from that, because this will be always there as you increase the current. But if you increase the current, it does not necessarily mean that you also increase the cooling power, because if you have high current but running it with a high delta T, or sorry, dt, then that means that you are not pumping heat, but you are just creating very large temperature difference between the two sides. So yeah, the larger the unit that you are using, so if you are using a 15 ampere unit, you have to run it at a higher current, and then you will produce more heat on the back side or on the hot side of it. So this is like, it's coming from the unit. And because of this P term, I was like pushing this kind of line in this direction. So if you remember, the smaller units were somewhere here, and then as I increased the amperes running through the certain units, then I had like the curves like this, and then this is a big jump here. I will create the summary video as well, and we will see how these numbers are lining up. But yeah, here you can see. And if I do the calculation, so I calculate the heat needed to change the temperature of the water from 29 degrees to 0 degrees, and the heat needed for the same action for the aluminum, then the sum of that two heats is roughly 4 watt-hours. And let's go to the voltage. So this situation is a bit tricky, because if you remember, or if you just go and see this number, the voltage was 14.6 volt, but that was measured at the beginning of the circuit. And then when I measured the voltage again at the banana plugs for the Peltier cooler, then I measured something like 10.9 volts. First of all, let's just evaluate the things at 10.9 volts, so let's say 11 volts, so somewhere here, and then I will tell you what's the problem. So roughly 10.9 volts, and this corresponding to 9 amperes, and this to 12, so we just have to divide this to 3 equal parts, so we are following roughly here, so something like this, something in this vicinity of this point, let's say. So we can conclude that we can draw a line here, something like this. So that was like, let's say 45 to 50, and then we push that up by 10, 15, 20. I just did here like 10. So the dt is 55. So we are, let's say, in between this area somewhere. And we can say that, okay, let's say that the dt is 55. So if we go here and check our 10 amperes, which is roughly here, then that's like 35 watts of cooling power, let's say somewhere here. And if we calculate our equation with the 30 watts, so if we provide 30 watts to this system, which needs 3.87 watts per hour, then it says that in roughly 8 minutes we can cool down the whole system to 0 degrees, but that's not correct. and then that suggests that we are way off with the cooling power. So then we can go like reverse engineer this, or just calculate in the reverse direction and see what we get. But instead of that, I want to explain that curious thing that I found. So what we have, basically, we have a power supply, and this is basically a DC power supply. My drawing will be very, very bad, but bear with me, please. So one rail starts and goes inside our box. Now I just draw a box, so this is not like a real drawing. And then the negative side also goes into the box. So we are here, and then inside the box we have the current meter, and that is basically connected to this part and then to the negative side of the Peltier unit. So that will be our big box here, and the positive side is basically just going through the box, and then by another cable goes to the Peltier. And then here we had the banana plugs, right? And I noticed in the video that this wire here was hot, and of course this as well. And when I measured the voltage between this point and this point, I got this 14.6 volts. But when I measured between this point and this point, then I got like 10.9. Well, what happens? So I have the power supply, just the DC power supply, and I have the load, right, which is the Peltier unit. And then here, and also here, there is a resistance, and this resistance is the damn cable. Because what happened is, if I measured it here, let's say between these points, I got this 14.6, and when I measured here, I got 10.9 volts. And what happened here is very funny. So now I think you can see what is this circuit, but this is a crazy voltage divider. So what happened is that let's say I'm measuring this at room temperature, like the cables are also at room temperature, then this voltage should show up here as well, because the effect of this circuit is just negligible. I checked it, and it doesn't drop the voltage, so that's not a problem. Or doesn't drop it very, very significantly, so it may be 0.1 volt or something like that, but it doesn't do anything. But then the cable here, and probably also down here, but let's just focus on this, because now we can see the circuit better. So that cable here, when we were at room temperature, then nothing was changed, but when this cable went up to roughly, I would say 60 degrees, because it was like really hot to touch, then of course the resistance changed, because this is a conductor, and if you change the temperature of a metallic conductor, then the resistance will be larger, and then you shift this voltage divider, of course, and this will look like something like this. And yeah, now this is just the ground, and I was basically measuring this voltage here with my voltmeter, and of course that was giving me some different values than this guy here, which is basically the positive side and the negative side of the power supply. So this is like very crazy that I was not realizing it when I started to observe this effect or phenomena, that basically I heated up the cables and I increased the resistance of it, and then therefore I changed this voltage divider. And in fact, we can have some rough estimation for the change of the resistance. So we know that we have the formula. So the voltage formula of this is V equals V power supply times R2, which is this guy here. So that's the Peltier unit's resistance, and R plus, let's call it R prime, plus R2. So R prime is this guy here, the wire. And we just rearrange this equation and we see that we have basically the following. So 10.9 equals 14.6 times this Peltier unit has roughly 0.9 ohms as a resistance, and then that is divided by R prime plus 0.9 again. So if we do the math, the R prime will be roughly 0.3 ohms. And then if I change this equation and I say that there is no voltage drop, or there is, let's say, just 0.1 volts voltage drop, which means that this voltage is changed to, let me continue it here. So that voltage is changed to 14.5 volts, then the R prime becomes 0.006 ohms. So you now see what's the problem. So we heated up that wire just like, let's say, 30 degrees, because the room temperature was 30 degrees anyway. So we went up to 30 degrees more in temperature, so to 60. And that changed the resistance of this cable by 0.3 ohms. And I can believe that that is like pretty much valid. And that changed our voltage divider, or actually created a voltage divider, because the system started to see a resistance here as a wire. And then that wire changed its resistance from, let's say, 0, this is basically 0, to 0.3. And that was just enough to like kick up everything and change the things. But that doesn't really change our observation, because of the wire and voltage divider, the Peltier unit was basically seeing this voltage and of course the same current, because we did not divide the current at all. This is a voltage divider at the end of the day, so this is still valid. But what was also valid, that it's very lucky that I measured this voltage as well, and now I actually also realized. So again, like in the previous video, we learned something new. So always oversize your cables, especially if you are running high current DC through your wires, because 10 amperes will literally light them up if you have thin wires. So yeah, be careful, because this is also a fire hazard. Of course, I was checking my cables and I knew that they should sustain the 10 amperes, but seems like at some cost. So we knew that 10 amps and let's say 11 volts was still running through this device. So maybe this number is a bit changed, but still, we saw that okay, based on these values and these values, we could get the QC, and we saw that that's not so precise. So sorry for changing the topic a little bit, but I discovered this. And if you try to recreate these things, you will always play with some wires and high current DC, and you will maybe not think about this thing. And I was not thinking about it. I was just aware of the fact that the wires become hot. And then I knew this, but I did not think about the effect on the resistance of the wire. But now I know, and now I can basically show it with a formula and some very, very simple calculation. Maybe these numbers are not so precise, but you can see the effect that this is like crazy. I mean, if you check it from the numbers perspective, then that is a factor of 50. I mean, the difference between this and 0.3. So if you increase the resistance by 50, then you can get some surprises. So yeah. So this was the final video of the test series. I will make another video where I basically summarize all these measurement data and try to provide you some useful data and some useful thoughts. And then I will still keep playing with these Peltier units, because I ordered some cool stuff to further extend my knowledge and my experience with these devices, because I think they are very fun to play with, and you can get some very interesting results. So I will keep playing with this, but for a while I will wait for these things that I have been ordering in the past few days. We have to wait for those things, but I don't want to spoil what is that. So if you want to check those things in the future, please subscribe the channel, and also give some comments, please, because I need some feedback about how is this experiment is going, and how did you like these things, and also if you discovered some very stupid mistake or something, let me know, because then I can make some corrections or things like that. So yeah, I hope that this video was useful or instructive to you, and see you in the next video.